Nanoscale innovation in progress. Imagine a world where computer chips don't just shrink, they evolve, smaller, faster, and more efficient, powering everything from supercomputers to smartwatches. The secret sauce? A microscopic layer of chemistry, photoresist. As we move into the era of 2-nanometer chips and below, traditional materials and methods used to etch silicon are becoming obsolete. Enter extreme ultraviolet lithography, the most advanced form of chip making. But even EUV has a critical bottleneck, the photoresist material. These ultra-thin films are what allow lasers to print tiny circuits on wafers. But the current generation of chemically amplified resists is struggling to keep up, plagued by blur, rough edges, and instability at smaller scales. That's why the industry is investing heavily in next-generation EUV resists, from metal oxide nanoparticles to resist-free etching techniques. These innovations could unlock faster chips, cleaner lines, and a sustainable path for Moore's Law. Before we proceed to the video, don't forget to hit the like button and ring the notification bell so you never miss our upcoming videos. Why resists matter more than ever? The challenge of shrinking nodes. Each generation of chips packs more transistors into a smaller space. But as line widths shrink to the size of molecules, precision becomes critical. EUV resists must maintain high contrast, minimal line edge roughness, and low stochastic defects, a tall order for today's polymer-based cars. A 2023 study by the IMEC research group showed that below the 20-nanometer pitch, current CARs begin to suffer from acid diffusion issues that blur features and lower yield rates. A single misplaced line can ruin an entire chip. Manufacturing speed and yield. Today's EUV tools can only print a certain number of wafers per hour. Poor photoresist performance means manufacturers must increase exposure doses, reprocess wafers, or use double patterning, all of which raise costs and slow down throughput. Next-gen resists with higher EUV sensitivity allow for lower doses and faster patterning, which translates into higher fab efficiency and lower cost per chip. Environmental and industrial impact. Modern fabs consume thousands of gallons of chemicals daily. Resists with lower outgassing and recyclable components could significantly cut waste. Additionally, materials with longer shelf lives and better coating uniformity reduce product defects and chemical usage, making advanced lithography not just smarter but greener. Next-gen resists. What's changing? Chemically amplified resists, CAR 2.0. While traditional cars use organic polymers and photoacid generators, PAGs, new versions are using ultra-fast PAGs with reduced diffusion radii. These tweaks enhance resolution without increasing line roughness. Researchers at Tokyo University recently reported success with a polyhydroxystyrene-based resist with improved thermal stability and acid control, demonstrating 13 nanometers half-pitch line formation with minimal LER. Metal oxide resists. Metal oxide resists, made from elements like hafnium, tin, or zirconium, offer superior EUV absorption. These materials don't rely on acid diffusion. Instead, they solidify directly upon exposure, reducing blur and improving edge clarity. The benefits? Better line edge control, higher resistance to plasma etching, lower exposure doses. A collaborative project between ASML and IMEC showed hafnium-based MORs achieving 16 nanometers half-pitch with fewer stochastic defects than CARs. Resistless lithography. In cutting-edge labs, researchers are questioning whether resists are needed at all. Resist-free patterning uses EUV photons to directly modify the wafer's surface, or a sacrificial oxide layer. Stanford's Applied Physics Lab recently demonstrated EUV-induced oxide growth at nanoscale resolution, bypassing photoresists altogether. Though not ready for full-scale adoption, Such methods may be ideal for specialty chips or atomic-scale etching in the future. Hybrid and directed self-assembly. A fascinating area of research blends organic and inorganic chemistry. Hybrid resists combine the flexibility of cars with the stability of metal oxide structures. Meanwhile, block copolymer directed self-assembly uses pre-patterned EUV features to guide nanoscale phase separation. This method promises ultra-high resolution for DRAM, NAND, and logic, allowing more data to be stored in a smaller space. Real-world deployment and industry moves, IBM and Intel trials. Both companies have been testing hybrid and MOR resists in 3 nanometers and sub-3 nanometers processes. IBM's Albany Nanotech Center has demonstrated 10 nanometer pitchline space arrays using tin oxide resists, signaling commercial readiness within 3 to 5 years. ASML's scanner optimization. The Dutch firm behind EUV scanners is tailoring its latest generation of tools, NXE3800E, to optimize compatibility with next-gen resists. Faster wafer stages and improved dose control complement the use of lower sensitivity, high-contrast materials. Global startup ecosystem. Startups like Inpria, acquired by JSR, are at the forefront of MOR development. Others, like EUVend, are working on custom formulations tailored for logic or memory use cases. Many of these new materials are being co-developed with fabs, ensuring rapid qualification and deployment. What's holding things back? Complexity in development. Designing new photoresists isn't just about chemistry, it's about the entire ecosystem. Developers must consider etch compatibility, post-exposure bake dynamics, pattern collapse risks, and residual resist contamination. High cost of qualification. It can cost tens of millions of dollars to test and qualify new resist formulations for high-volume manufacturing. This creates barriers for small innovators unless partnered with foundries or large tool makers. Variability in results. Even minor changes in humidity, tool settings, or substrate flatness can dramatically impact resist performance. Uniformity and consistency across thousands of wafers are still a major challenge. The road ahead, a pattern for the future. The next 5 to 10 years are critical. Experts believe that by 2027, metal oxide and hybrid resists will be widely used for 2 nanometers and 1.5 nanometers nodes, particularly in leading-edge logic chips. By 2030, we could even see resist-free etch techniques entering high-value custom chip production. Semiconductor giants like TSMC and Samsung are investing heavily in resist R&D alongside public-private partnerships across Japan, South Korea, and the EU. In fact, the European Union's IPCEI initiative has designated advanced lithography materials as strategic components of chip sovereignty. The invisible revolution. The photoresist may be invisible to the naked eye, but it's one of the most powerful materials in the world, determining how fast our phones run, how efficiently our servers operate, and how much data our chips can handle. From chemically enhanced films to resist-free processing, the industry is rewriting the rules of chip making, 1 nanometer at a time. In the race to extend Moore's Law and meet exploding global demand for AI, 5G, autonomous vehicles, and cloud computing, next-generation EUV photoresists may hold the key. Whether it's metal oxide particles or photon-triggered chemical shifts, the tiny film layered on a silicon wafer could define the next decade of technology. If you enjoyed what you saw, don't forget to hit the like button and ring the notification bell so you never miss our upcoming videos. Your support means a lot to us. Take care until the next one, and feel free to drop a comment sharing your thoughts. See you soon.